Hello, everyone. In today's class, we will be looking at growth and decay and separation of variables in our chapter, Differential Equations. The topics we will be covering is to recognize and solve a differential equation using a separation of variables approach. And then we will also be using exponential functions to model growth and decay in applied problems and in other kind of applied problems too. And then finally, we'll be looking at analyzing and solving logistic differential equations. So the first thing we're going to do is we are going to look at separation of variables. It is a strategy in which we rewrite the differential equation so that each variable occurs on only one side of the equation. So formally, the definition is, if we have a differential equation, which can be written in the form of dy by dx equals mx over ny, and then we just basically take the ny and the dy together, just like a little simple cross multiplication if you want to think of this way, ny and dy, together, and mx and dx. That's one simple way of looking at it. So your m is a continuous function of x alone, and n is a continuous function of y alone. So those kind of equations are said to be separable, and the solution procedure is called separation of variables. Let's look at an example. Say dy by dx equals 2x over y. Then we'll combine the y's together, so y and dy. That becomes the left-hand side of this equation, and 2x dx becomes the right-hand side of the equation. Let's look at some further examples. Suppose this is the original differential equation, x squared plus 3y dy by dx equals 0. Now I want to write this in a separable variable form. So the first thing we're going to do is we're going to take the x squared on the other side. So this becomes 3y dy by dx equals negative x squared. And now remember, y's are together, need to just take the x with the dx. And then we get this equation, 3y dy equals negative x squared dx. Okay, now let's look at the differential equation, sine x y prime equals cosine x. Different ways of writing a differential equation. So this one can be written as sine x then dy by dx equals cosine x. And then what we're going to do is take the sine x, because we do not have any y's, so sine x has to be taken on the right-hand side. So we get dy by dx equals cosine x over sine x, and we know cosine x over sine x is nothing but cotangent x. So thus, our new equation in the variable separable form is dy equals cotangent x dx. Okay, that was the second example for a variable separable. Now let's look at the third example, which is xy prime divided by e to the power y plus 1 equals 2. Now, we can rewrite this equation as x over e to the power y plus 1, then you times dy by dx equals 2. Now, ey plus 1 is with your dy, and x will be taken here. So we can write this as 1 over ey plus 1 dy by dx equals 2 over x. And then just keep the y's and the x's together. So you get this 1 over ey plus 1 dy equals 2 over x dx. Very simple, guys. Now we are going to solve a differential equation, a very simple one. Y prime equals dx over dy. Or we can write it in a different form, and that is dy by dx equals 2x over y, and then just get the dy's and the x's together. So y dy equals 2x dx. So I want to solve this. That means I want to find, solving a differential equation, remember, means finding y. Okay, that is the solution of a differential equation. So then we integrate both the sides of this equation. We get half y squared equals x squared. Remember, when we're integrating, we will always add a constant in the end. And then just doing simple algebra, y squared equals 2x squared plus 2c, or I can write this as y squared minus 2x squared equals 2c. Remember, c is a constant, 2 times c is another constant. I'm just calling this constant a k. So final answer for this differential equation, y prime equals 2x over y, is y squared minus 2x squared equals k. Well, we're going to start with growth and decay models. Now, there are many applications where the rate of change of a variable y is proportional to the value of y. Now, remember, rate of change means you're using dy over dx. That's the meaning. When I say the word proportional, it's simply, this means proportional. This is the symbol for proportional to the value of y, proportional to y. So this is basically the sentence saying that there's a change in the variable y. The rate of change in the variable y is proportional to the value of y. Now, when we write it in a proper mathematical, way here, so when we're saying is that dy by, so x, rate of change. So you can have, if it's not x, it can be t. So I can say dy over dt. It doesn't matter. It's a variable, guys. It's an independent variable. And most of the time, the applications, your independent variable is time. So that is why we write as dy over dt. It's proportional to y. Now, the way we remove the proportional sign and we write this as dy by dt equals k times y, where my k is a constant. Okay, so the rate of change of y, remember, is a differential, is proportional to y, means equals k times y. Now, so here is our just an overview of our growth and decay models. And we have something called the exponential growth and decay. Now, if it says this, if y is a differentiable function of time, say t, such that y is positive, and then dy by dt is equal to ky. Now, we're assuming that y is positive. For some constant k, then y equals c e to the power kt, where c is a constant, it is the initial value of y. K is called the proportionality constant, and the exponential growth will happen when your k is positive, and exponential decay will happen when k is negative. Now, we have learned the variable separation technique. We can apply to this equation and see that we will get this as our solution. So let's do it here. So if I say dy by dt equals k times y. Okay, now remember, variable separable means get the y's together. So it's 1 over y dy equals k times dt. Now we're going to integrate. So because remember, we're finding the solution, y over dy equals integral k dt. So when we integrate, remember, integral of 1 over y dy is natural log of absolute value of y. Remember, your y is a variable and you want the y to be positive. So that's why you're using absolute value of y equals k times t. Kt plus a constant. Okay, now keep in mind this one. Now, if I remove the natural log, we have y equals e to the power kt plus c. Now I'm going to do some simple algebra here. It is e times kt times e to the power c. And now e to the power c is a constant. Remember, c is a constant, e to the power c is also a constant. So let's write this as, say, okay, let me make it easy, say C1, because I want to be little, say, kind of consistent with this. solution given to us. So C1 and C1. So I'm going to say this one is say e to the power kt times say C2. So what I can write is, I can just, write constant in the front, C2 e to the power kt. Now, if my y is positive, then, remember absolute value, if I remove the absolute value, it's going to be a plus minus. So y equals, now, or if I take my y to be positive, then that means absolute value of y will always be y. This will be equal to C2 e to the power kt. Or I can rewrite this as y equals c to the power e kt. Another way of looking at that is this. So this is one way here, because I'm assuming y is positive. So I'm trying to get the solution. Or also I can say that if I remove your absolute value of y, another way of looking at is C2 e to the power kt. If I remove the absolute value, because your y can be positive, negative, I can write this as y equals plus minus C2 e to the power kt. A plus minus with a constant is still going to be a constant. So I can write this as y equals, say, another constant, k e to the power kt. Okay, remember, c, k, each one of them is a constant. Bottom line here is that if you're given an equation, a differential equation, dy by dt equals ky, the solution for this one is given as y equals a constant e to the power kt. That's what we need to remember. And that k is the proportionality constant. If the k is positive, that means there's exponential growth. And if k is negative, then there's exponential decay. Now, if you remember this exponential growth, let's look at exponential growth. How does a graph look like? Exponential growth, remember, suppose that means when k is positive. So this will be, for a very simple, say c is 1. So it's y equals e to the power k t, okay? And if I'm taking this one, this is how a growth looks like. So when your t is 0, your y is 1. So this is my t and this is my y. Or if you look, let's look at exponential decay. Once again, here my c, suppose, is 1, and my k is less than 0, okay? So when k is less than 0, that means it's a negative, so any negative value, the graph will look like this. That's exponential decay. So this is y equals e. Suppose let's take k to be -1. So negative t. Or over here, if I'm taking, say, k to be, I can take k to be 1 also here. But the big picture is when it is exponential growth, you have a curve which is going up. And when you have an exponential decay, you have a curve which is exponential curve, right, which goes down. So both sides, it's an exponential curve. Now, let's look at a very simple exponential growth model. We are given that the rate of change of y is proportional to y. That means my differential equation is dy by dt, because we are having when t is here and y. So I'm going to assume, I'm just taking t to be the independent variable, is k times y. And we just learned that the solution of this equation, say 1, is given by solution of equation 1, we just looked at it, is given by c equals, y equals c e to the power k t, okay? A k is a proportionality constant, that's it. Now it says when t is 0, now I want to find the solution, okay? What is the value of y when t is 3? So first thing was, we're given that the rate of change of y is proportional to y, and then we're given some initial conditions or conditions. When t is 0, y is 2. When t is 2, y is 4. And the question is, what is the value of y when t is 3? Now, to do all of that, notice so we need to find our c and we need to find k. So in order to find this, answer this question, what is the value of t equals 3? What we need to do is we need to find c and k. These are two constants. Now, if there are two constants in an equation, we need two conditions given to us. So one condition is this, and the other condition, when t is 2, y is 4. Okay, so let's start with the first one. When t is 0, we are given y to be 2. Let's put this in equation 2. Okay, substitute these two values into. So we are substituting in equation 2. What do we get? T is 0. So we get 2 equals c e to the power 0. Anything to the power of 0 we know is 1. So c is 2. So what is our equation now? Y equals 2 e to the power kt. Now let's look at the next values. It says when t is 2, y is 4. Okay, so 4 equals 2 e to the power k times 2. Or this is 2 equals e to the power 2k. Now, we want to find k. Now we know that exponentials and logarithms are opposites of each other. So we can write this as natural log of 2 equals natural log of e to the power 2k. Our logarithm properties are 2k comes out, natural log of e. Now, if you remember, natural log of e is 1, is 2k is natural log of 2, or my k is 1 over half 2 natural log of 2. So it's approximately, it is so it's 0.3466. So our y, the solution, which is given by equation 2 for the differential equation. So now the solution with finding out c's and k's becomes, c is what? 2 e to the power 0.3466t. Now we can find the answer for what is the value of y when t is 3. So when t is 3, y is what? 2 e to the power 0.3466 times 3, approximately 5.6567. Okay, so this was a very simple exponential growth model. Now let's look at an exponential decay model. The problem is given by, it's a plutonium isotope problem. So let's read the problem now. 10 grams of the plutonium isotope, which is 239Pu, were released in a nuclear accident. The question is, how long will it take for the 10 grams of this plutonium to decay to 1 gram? And the hint is that the half-life of this plutonium is 24,100 years. Okay, half-life, let me explain what half-life is first before I start with the problem. So when I say half-life, half-life means that as of today, we are saying that the plutonium is, so today T is T, the plutonium gram is 10 grams. So half-life means how much time does it take to become 5 grams? So according to the information given, that it takes 24,100 years for 10 grams of plutonium to decay to 5 grams. Okay, so that is the key. So 5 grams of this plutonium will take at least, minimum of 24,500, not minimum, it takes these many years to become to 5 grams. Okay, now let's start the problem. So how long, so we're going to say is let, so I'm going to start with the solution now. Let Y represent the mass, which is in grams here, of this plutonium 239 Pu. Okay, we are given now the rate of decay. Remember the exponential decay model? The rate of decay is proportional to the value of rate of decay is proportional to the value of Y, where my Y is basically the mass. So remember, the rate of decay is proportional to Y, because we're doing these exponential growth and decay models. So the differential equation means dy by dt is equals k times Y. Okay, now we also know the solution of the star is given by Y equals C e to the power kt. Okay, now to find how much time it will take, first of all, we have to find the C and the K's. Now, it says when some accident happened, a nuclear accident, 10 grams actually were released. So that means that's the starting point. It says when time was 0, when the whole process started, there was 10 grams of plutonium. So substituting it over here, what we see is that 10 equals C e to the power k times 0, or C e to the power 0, or C is 10 grams. Okay, so now my solution is given by 10 e to the power kt. Now, k, remember, is what we have to find now. Now, what was the other thing we knew? The half-life of this plutonium is 24,100 years. That means when T is 24,100 years, my Y is 5 grams. So let's write it down. When T is 24,100, my Y is 5 grams. So substituting, 5 equals 10 e to the power 24,100 T, which is half e to the power 24,100 T. Now remember, we already have done all the steps, so I'm just going to take the natural logs. Natural log of 1/2 equals 24,100 T. Natural log of E, which is 1, which is 24,100 T. So now 1 over 24,100 times natural log of half equals T. Your T is approximately, I'm so sorry. It's not T, it's K. Yeah. I'm so sorry, guys. Yeah, it's like something is not right. Yeah. So it's K, guys, please. Just go ahead. I'm just going to go. It's K because T was the one to be replaced. K. So K is approximately negative 0.402876. Okay, so now our solution is y equals 10 e to the power negative 0.402876t. The question is, how long will it take? Now we have got all our constants filled here. Now what we want to know is the time it takes from 10 grams to go to 1 gram. Okay, so now we come to the problem. How long? That means how much t, so that 10 grams becomes 1 gram. So 1 equals 10 e to the power negative 0.402876t. You can do the computational now. T is approximately 80,059 years. Okay, now let's look at another problem, which is the population growth model. An experimental population of fruit flies increases according to the law of exponential growth. The information is there are 100 flies after the second day of the experiment, and there were 300 flies after the fourth day. Approximately, how many flies were in the original population? So let's start the problem. First of all, what are we looking? We're looking at population is the variable. So we say let P be the population, because it's regarding population here. And what are we given? We are given that there's an exponent. This growth of fruit flies is the exponential growth model. That means we are having the differential equation dp over dt equals k times p now, because y, I'm not using y as the variable, I'm just saying p is the population, which is basically changing as time goes. Okay, so what is the solution? We already know the solution for this one is that p equals a constant, say c, e to the power k t. Okay, remember p represents the population. Okay, now what is the information? The second line, what does the second line tells us? That after the second day, there are 100 flies. That means when t is 2, the population of the fruit flies is 100. And then after the fourth day, there are 300 flies. Okay, what does that mean? It says that t is 4. Now remember, these are days we are talking about. The time is now in days. The population is 300. Its question is approximately how many flies were in the original. That means we want p sub 0. P sub 0 is basically original population. I'm just using it as a variable. So I want to find, or you can say that, what is the population p when t is 0? Okay. These are just notations, guys. Okay, let's now find, in order to find P0 or time 0, what is the population, we got to find first K and C. Using these two, values of T and P, we are going to actually find those values. So let's substitute T equals T, 2 and P equals 100 in this equation, say star. So substitute T equals 2 and P equals 100 in star. What are we going to get? 100 equals C e to the power 2t. Okay, and then because it still won't give us anything, we have to substitute the next option also. That means 300 equals C e to the power 40. Now we got these two equations. To find C and T, what I'm going to do is I'm going to look at this double star. So from double star, what do we see? that C equals 100 e to the power negative 2t. Okay. Now this C value, I will substitute in the equation with 3 stars. Substitute this one. Okay, let me just write it down. Substitute this in 3 stars. What are we going to get? 300 equals 100 e to the power negative 2t. Or 3 equals e to the power negative 2t. And which basically means natural log of 3 equals, did I do the right? Oh, no. Oh, I forgot, because e to the power 40, I mean, something was not right. Well, let me just write it nicer. Times e to the power 40. Now this is plus 2t. 2t and half of natural log of 3 times natural log of 3 equals t. T is approximately, are we doing t or, yeah, once again, I'm making the same mistake. It is the k, it is t is 2. So yeah, once again, guys, I'm still doing the same mistake. So it's a k, guys, I'm so sorry. Yeah, it's a t value which had to be replaced. Okay, sorry. So it is the k, which is now approximately 0.5493. Okay, well, I'm glad I'm finding my mistakes right when I'm doing it here. Okay, so what are we seeing now? So our population is C e to the power 0.5493 t, okay? But we got to find C also. Now to find C, I'm going to once again go back to the double star. So substitute this above equation, substitute the double star. Sorry guys, today I'm making a little bit more mistakes. So, okay. So we're going to substitute star in the above equation. Now, what are we going to get? So it says P is 100. So let's write down nicely. P is 100 when time is 2. CE, I'm going to be very careful now, times 2. So doing the math, my C comes out to be approximately 33. So now, the nicer little population solution to this differential equation is P equals 33 e to the power 0.5493 t. Now, remember the original population you have to find. So the original population means when t is 0. So what basically it means is t is 33. So that means the very first day the fruit flies started, there were 33 of them. Okay, so we have done some exponential growth and decay models. Another kind of problem we can also do here is something called Newton's law of cooling. Now, what is Newton's law of cooling? Newton's law of cooling states that the rate of change, okay, the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So here's the rate of change in the temperature of an object. So what is the variable we are looking at is the temperature of the object, okay? So you say let's write in a nice little, equation form. So you say let Y be the temperature of an object, okay? And this temperature of an object is the rate of change is proportional. Okay, that means dy by dt is proportional. That means k times difference between the object's temperature, which is given to be y, minus the temperature of the surrounding medium. So let the temperature of the surrounding medium, say, be capital T. Okay, so the temperature of the surrounding medium is capital T. And that's what it says here is the Newton's law of cooling. It says if Y, which is the temperature of object, according to Newton's law of cooling, the rate of change of this Y is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So this is our differential equation. And you notice we can easily do once again our variable separable approach here too, if you want to find the solutions to this one. Okay. So I'm going to take an example and then I will show you how to find the solution of this differential equation too. Now let's look at this example. It says if Y represents the temperature in Fahrenheit degrees of an object in a room whose temperature is kept at a constant 60° Fahrenheit. Okay, so the temperature of the object is kept at a constant. So that means, remember, the temperature of an object and its outside medium is what is this? It says Y is representing the temperature of an object, which is put inside a room which has a constant temperature of 60° Fahrenheit. Remember, according to the Newton's law of cooling, we look at the temperature of the surrounding medium. Okay, so this 60° Fahrenheit is the temperature of the surrounding medium, which is basically the temperature in the room. Okay, the next line says the object cools from 100 degrees to 90° Fahrenheit in 10 minutes. Okay, then the question is, how long will it take for the temperature of the subject to decrease to 80° Fahrenheit? So that means that we are looking at this whole temperature of the object from 80 degrees to 100 degrees. That's the value which my temperature of the object will take according to this word problem. Okay, so let's write down first the differential equation because it's a Newton's law of cooling. So dy by dt is k times y, remember, is the temperature of the object, and the difference between the temperature of the object and the surrounding medium, which is given the temperature in the room, y minus 60. And because the way the problem is given, we want to know how much time it will take for y to go down to 80 degrees from 100 degrees. So my y is between 80 to 100 in this problem for us. Now, clearly, if I want to find a solution to this differential equation, I will be using a variable separable form, getting the y's together and the t's together. So it is 1 over y minus 60 dy equals k times dt. Then we will integrate 1 over y minus 60 dy equals k times dt. Now remember, this is, we have done our differential integrals of natural logs. So the natural log, this is y minus 60, and I'm taking the absolute value, equals k times t plus a constant. Now you got to be careful because we're only looking at the temperature from 80 to 100. That means my y will always be greater than 60. So as the temperature is more than 60, so clearly the difference between y minus 60 is definitely going to be positive. So I can write this as y minus 60. So y, okay, so that's natural log of y minus 60. That means I can remove the absolute value equals k times plus c. Now I want to find y. Remember, the solution is y of the differential equation. So I can take the natural log out and then take the exponential on the other side. So it's exponential kt plus c, and this is y equals 60. Take the 60 on the other side, plus e times kt times, I can write this, the exponential laws, e to the c, which is a constant, or a nicer little equation is y equals 60 plus, say, c, e to the power kt. Okay, now, to find how much time it will take for the temperature to decrease to 80 degrees, I need to find my c's and k, the capital C and the k. Okay, what is the first thing given? When we started the problem at time 0, 100 degrees was the temperature. So y is 100 when my t is 0. Let's substitute. 100 equals 60 plus c e to the power 0, or 40 equals c. So our equation now is y equals 60 plus 40 times e to the power kt. Now the second line in this word problem says it takes 10 minutes to go down to 90 degrees. Okay, that means T is 10. When T is 10, the temperature is 90. Okay, so let's write it down. 90 equals, that means put this value up here, 60 plus 40 e to the power k times 10. I'm making sure I'm not making a mistake like I did last time. Okay, so now simple algebra, 30 equals 40 e to the power 10k, or 3 over 4 equals e to the power k, or k equals, 10k is 10k equals, removing the exponentials by taking a logarithm of the equation, natural log of 3 over 4. Okay, let's go to the next slide. So we had 10k equals natural log of 3/4, and our k is 110 times natural log of 3/4. Approximately, my k comes out to be negative 0.02877. So now my nice little equation is 60 plus 40 e to the power negative 0.02877 t. Now remember, the question says what? How long will it take for the temperature of the object to decrease? Like how much time more it is going to decrease to 80 from 90? That's what it means, because it started from 100 to 10 minutes to reduce to 90. I need to know how much more time will it take to decrease to 80. Okay, so let's go back to our problem. Now first we'll find out what is the temperature, or what is the time it takes to reach to 80. That's what first we're going to do. So when y is 80, we need to know how much is the time? Okay, so then substitution in the above equation, 60 plus 40 e to the power negative 0.02877 t, which is 20 equals 40 e to the power negative 0.02877 t, which is 20 over 40 half e to the power negative 0.02877 t. Doing more calculations, you can find that t is approximately 24.079 minutes. Now remember, this means it starting at when it was 100, it took 24 minutes to reach, approximately 24 minutes to reach to 80. But the question was saying, how much longer, okay? How much longer will it take for the temperature to decrease to 80? Okay, let me repeat the whole sentence, the last two sentences, which will make it more clear why I'm writing the answer as it is. The object cools from 100 to 90 in 10 minutes. Then it says, how long will it take for the temperature to decrease to 80 degrees? Or how much longer will it take for the temperature? How much longer will it take for the temperature? So coming back, remember, it took 10 minutes to go to 90 degrees. Now it takes 24 minutes to go from 100 to 80. So how much longer? After 90 degrees, that means T is 24.09 minus 10. It takes approximately 14 minutes till 14. So let me write it down. It will take 14 more minutes for the object to cool to 80 degrees Fahrenheit. Okay. Now, the picture on the left-hand side actually shows how the temperature is going down. So the question is, how much more time will it take to go from 90 to 80? That means 14 more minutes. Okay. Now, the next thing as we do some examples is practice problems. So the next 2 slides gives you a problem. The similar kind of problems I have done as examples for you. So first do the examples and then definitely try these problems. Thank you.